Hello, greetings, people. My name is Aaryan Dubey, and I'm going to present on LIMO. Less is more for reasoning. So let's see what it is, right? So I think guys might have seen Dragon Ball, right? I don't know how many of people have seen Dragon Ball. So you have seen Goku going Super Saiyan first time, right? On that planet, and Frieza, okay, Super Saiyan. So it's like Goku always had this Super Saiyan inside him, right? But no one had the power. Okay, take it out. But that situation made him take it out, that power, right? An adrenaline boost. So considered LIMO a kind of that thing. So let's see, an LM has a lot of knowledge, right? They just put it math book, math paper, everything. But what LIMO does is that it's going to teach LM, okay, you have the math book, right? So I'm going to teach you how to solve this math problem step by step. I don't know, in exams, you might have seen, okay, you need to solve a math problem. So they give numbers on if you write step by step how to solve a problem, or a physics problem if you solve it. Because, okay, if you write the steps, you'll get more marks instead of just putting answers there, right? So it's like this. LIMO tells you, okay, if you give it like this step by step. So, okay, answer is F. So what is the step? A, B, C, D, E. So to reach F, you need to go A, B, C, D, E. So that is the step to go to F. That means you can extract that knowledge and teach LLM how to solve a problem by thinking like human, the cognitive skills of a human, our thinking process. So that's what LIMO is. Goku going Super Saiyan means something extracted that power from him, right? So LIMO does that. It extracts that power from LLM and say, okay, you can solve this problem even if you can't earlier see. These are the steps. Then you will kind of overfit it on a math problem. Then if it overfit, it's learn how to think, right, during that overfitting, right? And then if you give it a new problem, it will try to solve it on its own. And in most of the cases, it thinks and it will able to solve it by incorporating a thinking process. So in short, this is LIMO. But let's see, deep dive into the paper and see how it goes. So what it is, so it will bring out the powers of reasoning from the LLM. So it goes for the cognitive templates, as I showed you guys. I need to give few examples to solve a problem. So what did they assume? They assume that we need a lot of training data to solve a problem. The basic principle of whole machine learning or data science field, right? But LIMO said, no, in that training data, we can teach it to think and show some thinking skills on unknown data set. So they go for this cognitive scaffolding, right? So each steps contain explanation. So if you want to solve a physics problem, so if you want to define gravity, you'll be like, okay, this is the equation for gravity. How does it come? How was it discovered, or something like that? So each steps contain explanation. Concept should be connected. So A is connected to B, B is connected to C, C is connected to D, D is connected to E, and then is the solution F, right? You should double check every solution like we do, right? So when you type a solution or write a physics equation or math, you should always check, okay, this step is good, this step is bad, this step is good, something like that. So it's like this. Think like human. LIMO does that. Cognitive scaffolding, okay. Think like human, LLM. Let's go into the hypothesis. Less is more reasoning hypothesis. So in foundation models where domain knowledge has been comprehensive encoded during the pre-training, right? Sophisticated reasoning capabilities can emerge through minimal but precise orchestrated demonstration of cognitive process. So the completion of the model's encoded knowledge foundation during pre-training and effectiveness of the post-training example, which serves as the cognitive templates that shows model how effectively to utilize its existing knowledge base to solve a complex reasoning task. So you have a dictionary, right? Let's imagine you have a dictionary. And LIMO will tell you, okay, this is how you look through dictionary. Okay, A, B, C, D to alphabetic order, something like that. And you can solve it. Once you only have a dictionary, you don't know how to look through a dictionary, you won't be able to solve it. What LIMO does that, okay, read the dictionary, Arvin. You'll be able to learn the meaning of that word. Or you can just Google it, but that's a different thing. But yeah, that's more or less what abstract tells you about the whole LIMO. Less is more for reasoning. They say that they use only 817 curated training samples. Like after if we deep dive into the paper, we'll see like how these 817 curated training samples are created. Spoiler alert, AI, they use the AI there too. So LIMO achieved 57% for accuracy on highly challenging AME benchmark, which is more than 94% on math, that is another data set. And absolute improvements upon 10 diverse benchmarks are performing trained model on 100x more data. You can see they described it here, etc. It's open source. I was reading through the GitHub. It's a quite comprehensive repository you can go and see. And they supervise, fine-tune the whole model. So that's very interesting using this 817 curated training samples. I think it's the Queen 32B instruct model that they fine-tune it, but let's deep dive more into it to understand it more. Awesome. We reached the introduction part. So introduction. So teaching model to reason, particularly in mathematics or programming, is widely believed to require vastly more training examples, right? Everyone will say, okay, we need a hell lot of training data to train this model, but no. They say that fundamental reimagining how we approach reasoning in LLMs. They say there are two ways: knowledge foundation revolution and inference time computational scaling revolution. So knowledge foundation revolution says that we have a lot of data as an LLMs, right? So they possess rich maths knowledge and knowledge acquisition to knowledge elicitation. Simple means you have the knowledge, will teach you how to extract that knowledge or think to get that knowledge. Other is inference time computational scaling revolution. They say that extended reasoning chains significantly improves their reasoning availability. So inference time computation provides crucial cognitive workspace for unpacking and applying this pre-trained knowledge. So you run an LLM, then it starts thinking. So in that time, you need to have a lot of resources, etc., so it can think, it can produce that. So it takes time. So they say that we need an inference time computational scaling revolution that kind of happened in 2 years, they are saying, because they are building on the foundation of LIMO from Facebook, and they say that LIMO was created 2 years ago, and it took 2 years time to reach this inference time computational scaling revolution. They say that hypothesis is successful reasoning, rich pre-trained knowledge, and sufficient computational resources at the inference time. So model, they say a lot of it. This model possesses rich reasoning knowledge and are given adequate computational space. Then activating their reasoning capabilities may require only a small number of high training quality samples. This makes them produce LIMO, as you can see in bold here. Less is more for reasoning. So this hypothesis identified two crucial factors determine an elicitation threshold for complex reasoning. First, the latent presence of pre-existing knowledge within the model parameter space, right? That knowledge should be present, right? The effectiveness of minimal example in demonstrating the systematic problematic solving process that encourage extended deliberation. So let's see a simple example which I thought or taken from GPT, right? So what is 8, even or odd? Answer is even. Simple, nothing, right? You give it an example, right? Then it will go to the reasoning step, what LIMO is saying, kind of. So you provide just one careful design problem, but force AI to reason through it. So question is 8 even or odd? Solution breakdown. Step 1, an even number is any number that can be divided by 2 without a reminder. Step 2, divide 8 by 2. 8 divided by 2, 48 by 2, 48 by 2, no remainder. Steps, since there is no remainder, 8 is even. So something like that. So they say we establish the LIMO hypothesis, demonstrating that complex reasoning capabilities can be elicited through surprising small data. So elicited means it can be taken out or make it learn, etc. Hundreds of examples by leveraging rich mathematical knowledge in pre-trained models and detailed reasoning chains. So they say that we provide systematic empirical evidence challenging the current assumption about scaling laws in reasoning tasks, showing that benefits generalized robust to out of distribution problem is suggesting that acquisition of genuine reasoning capabilities. So that's generally part of the introduction part of this. And then we move towards the second part of it. You can read through this complex reasoning, LIMO, etc. That will be looking more towards it. But then we go to phenomenal rethinking, less is more, and reinforcement scaling, where it generally comes through here. Phenomenal rethinking and less is more in reinforcements thinking. So less is more hypothesis. AI can learn deep reasoning with fewer high quality examples rather than massive data set. And after that, we have reinforcement learning scaling, which is very hot in today's scenario, right? So AI can learn reasoning without extensive retraining by thinking better in inference time, etc. So they say that in this phenomenal rethinking, less is more reinforcement scaling. Then we go for LIMO versus LIMA, right? So LIMA requires test time scaling techniques so it can think deliberately. So reasoning elicitation threshold. So when model possesses both rich domain knowledge and sufficient computational space. Complex reasoning capabilities can be activated with minimal but precise demonstration. It took time to achieve this. What they say in this LIMO versus LIMA, simple and easy. And after that, they could try to compare with this like LIMO and reinforcement learning scaling. As LIMO is kind of what reinforcement learning tries to do. They say like why it's different, why we are better, or why it could be different. So in simple terms, they say that it assumes that reasoning capabilities needs to be extensively trained into model through large-scale reinforcement learning, right? That's what reinforcement learning does. Reinforcement learning discovers effective reasoning patterns through massive computational resources. But LIMO thinks reasoning capabilities are already latent with pre-trained models. So training to elicitation, finding precise cognitive templates that can elicit these innate abilities, right? So simple. Instead of saying, okay, should we train it? No, no, no. We should illustrate that knowledge. So a cognitive template that can take out this knowledge is better than going to the reinforcement learning approach. That was they say, like implicit trajectory discovered through large-scale reinforcement learning optimization. Explicit trajectory designed through cognitive templates. So that's what it is. They say that computational capability revolution that I told you about, like how we can compute at the test time. Then reasoning elicitation threshold, when model possesses a rich domain knowledge and sufficient computational space, complex reasoning capability can be activated through minimal precise demonstration. And then reinforcement learning scaling, which I showed you guys in the table. Then we go for the main thing, the LIMO data set. What it does is that. So they say that unlike traditional AI data set, which contain millions of training examples, LIMO data set is very small. It contains only 817 high-quality training examples were used, right? And high-quality reasoning chain. Every example has detailed step-by-step solution. Like every math example that they're trying to solve, they have said, okay, this is how the steps were going to go, as I explained in the earlier part of the presentation. And designed for maximum learning. AI learns to think, just not what answers are. It's not like this, A is equal to B. No, no. How A is equal to B, how left-hand side is equal to the right-hand side, something like that. So instead of making AI memorize answer, it learns systematic reasoning, which I think is very important. So more structured examples is equal to AI generalize better to a new problem. So these are the things that LIMO dataset generally defines. Then we go towards the question selection. So they say that level of difficulty, we prioritize challenging problems that foster complex reasoning chains, diverse thought processes, knowledge integration, and enabling LLMs to effectively leverage this pre-trained knowledge of high-quality inference. So generally, problems that deviate more from model training distribution can better challenge its fixed thinking pattern, encourage exploration of new reasoning approaches, thus expanding its inference search space. Knowledge diversity, the selected problems covers various mathematical domains and concepts, requiring the model to integrate and connect distance knowledge during the problem solving. So whether the sources from mass competition, AME, maths, Olympiad level problem include the mix of algebra, number theory, geometry, combinatorics, anything you can find. So after that, what they tend to do is that the systematic multi-stage filtration process. Let me see. You can see problem definition here, reasoning task with verifiable answer. You can see what they define it, questions, answers, reasoning chain, etc. Define this formula, etc. Which I don't think so. They use it anyway, just define it here properly. High quality data curation, data set is quality reasoning answer, when as the number of intentionally kept small to well data LIMO hypothesis. As I defined the question selection to you guys just now. After that, we go for the main part, reasoning chain construction. So how does it go? So beyond high quality questions and quality of solution and comprehensive selection strategy, we begin by gathering official solutions for problem where available, right? It could be anything. We leverage state-of-art reasoning models, DeepSeek R1, DeepSeek R1, Coin Distill, Coin 32B, Coin 32 instruct to generate diverse solution approaches, right? After that, they use self-distillation techniques, Coin 2.5 instruct to create additional model variants, which were then used to generate supplementary problem responses. So first, they have a solution authored by human experts, then AI specialists. Then AI specialists is generally, I believe, DeepSeek R1, DeepSeek R1 Distill Coin 32B. Then they have Qwen232 be instruct to generate diverse solution approaches, then self-distillation technique on this model to generate additional model variants, which again generate samples of the solution. After that, they have these three things: optimal structural organization, effective cognitive scaffolding, and rigorous verification. In simple terms, it's this. So we have a solution, right? And we have to have the solution should be properly structured, not like, okay, A, B, C, D, F. No. Solution should be A, B should be connected to B should be connected to C, something like that. So granularity in step decomposition, particularly eloquates more token and detailed elaboration at crucial reasoning junction while maintaining concise expression for straightforward step. This self-adaptive approach to step granularity ensures that complex transactions receive appropriate attention while avoiding unnecessary verbosity. After that, effective cognitive scaffolding. High-quality solution provides strategic educational support and careful structured explanation. So every step should have an explanation. So A is connected to B is connected to C. Why? So you should have this reasoning. Okay, A is connected to B because of this theory, and this is the multiplication theory, or this something like that. This two matrix should be multiplied because it's written there, and this is there. And after that, rigorous verification. High quality solutions incorporate extremely frequent verification steps to reasoning process. So we should verify, okay, A is connected to B is connected to C because of this reason. Should we verify the solution? So we should have a verification cognitive thinking there too. So that's how this reasoning chain construction goes through. So in the end, it's like this. LIMO careful design its reasoning chain to follow this principle. Difficult steps to get more explanation details. Simple steps get short and clear statement. LLM learns structured reasoning, not just answer. Improve accuracy on hard problems where logical steps are crucial. Reduce unnecessary verbosity, making AI-generated solution more efficient. And enhance generalization, helping AI reasoning to the new problem. Simple. Less is more. High-quality demonstration. The resulting dataset consists carefully curated triples, while each reasoning chain are satisfy the quality criteria, which is this. Any questions till now? Oops. Okay. Methodology. Training protocol. So based on less is more principle, a model with substantial reasoning knowledge from pre-training and ability to perform long-chain reasoning, testing can develop robust reasoning skills. So training protocol. So they fine-tune a Qwen 2.5 32 billion supervised fine-tuning on Lima dataset. Training process had two things: full parameter fine-tuning, which is very interesting. Because when I started reading the papers, I thought, oh, it's not a full parameter fine-tuning, maybe some prompt or RAG-based scenario, something like that. But yeah, full parameter fine-tuning with deep speed 03 optimization and flash retention 2 with sequence length limit of 16,384 token. After that, we have the evaluation framework. So there's two evaluation framework that they do: in-domain evaluation and out-of-domain evaluation. In simple, I'll explain what this is, but let's move forward towards it. I'll explain it afterward. So performance metrics are this. We evaluate the performance using path@1 matrix. That is the first solution that the any LM produces. They'll just put it there. They said that for the sum data set, we use grading decoding. That means they didn't went for like, okay, if 5 or 10 solutions, then we see the best solution, something like that. First solution, take the one solution and access it and a single sample. And for the sum, they generated 16 samples where they have these computational knowledge, etc. They can. After that, they do the experiment. Experiment on what? OpenAI O1 preview, Qwen 32 billion preview, Qwen 2.5 they instruct, which serve as a base model with comparative analysis. Also keep in mind, this is the model which they self-fine-tune, right? So after that, they use different criteria, etc., different main results. So let's go back to the main results, like in-domain performance and out-of-domain generalization. In-domain performance is let's say we are trained it on a math data set, etc. So they try to see, okay, what's related to that maths problem, we'll try to solve, etc. Some AE Math Olympiad data set. So we'll try to kind of like an overfit, but not really an overfit. We can say that in that scenario, but out of domain means the problem should be a little bit different on how the model is trained on, etc. Right? So after that, they say that LIMO achieves highest average performance on 72% across all benchmarks, substantially outperforming OpenAI preview 01, Qwen 32 billion preview, and other baseline. Let's skip this part and let's go here. In domain, out domain. In domain, they tested on 3 datasets, AME24. If you go to the GitHub, you will see AME25 where they also tested it. I haven't seen the result yet, but they said, okay, AME25 is also tested right now, I believe. But yeah, AMC23. So LIMO, only 817 dataset. You see, it's the best one here, 57. Here it's 94.8. More than what? What? 9% more than that? Almost 10. AMC 23, 92. So it's one of the best. And out domain, it failed on Menvera and QPQA. Other than that, that's the best out there. So yeah, that's the particular result, the main results. Then we go towards analysis of these results. IQ1, impact of reasoning quality change. What is the impact? What is the etc., right? So let's start with this, right? How does the quality of reasoning chain impact AI models' ability to solve the problem, right? So they say that experiment to test whether better structured solution led to better AI performance. So high quality reasoning, better AI performance. So they took it for the 5 levels, right? We'll say, okay, 5 levels of reasoning quality: L1, L2, L3, L4, L5. So L5 is the best. Okay, we have all the reasoning, etc., etc., etc. You can see here. They write it. L5 solution are those showing excellent organization with clear, well-explained thought self-verification. And they just remove this small part. L4 solution were also well-structured, but perhaps slightly less rigorous checking. L3, more. L2, more data gone, more structured solution gone. L1, simple as anything you can imagine. As you can see the results here, Polar Alert is the best. L5 solution is the best. L4 solution little bit best. L3, L2, and L1 is the worst, right? That's what they say. L5 solution performed the best. L1 solution performed the worst. Difference between L5 and L1 was about 15% in accuracy. That means the structured solution and the reasoning quality chain, the reasoning chain quality is the best, and that's why it's performing best. But after that, we go for impact of question quality. That means your question quality should also be good. So hypothesis that training on more difficult, high quality problems improve AI reasoning ability. So to prove it, researchers tested on different types of training questions, grouped them into 3 difficulty levels: simple, complex, advanced. So 500 simple randomly selected problems from math level 1 and 2. Complex 500 complex problem randomly selected from math level 3, 4, 5. And 500 advanced randomly selected from past AME test. So spoiler alert, what could be the answer? AI trained on harder question, advanced 500, performed the best. Let me show you guys. Here is the graph I just showed. Advanced 500 is the best, and simple 500 is the worst. Complex 500 is the intermediate one. Yeah, that's the basic. And then they use DeepSeek R1 to generate solution, which represent high quality solution. Each problem set forming the training data for fine-tune Quen 3.2.532 billion instruct. What else? So now we have LLM backbone, the RQ3. So they say that model pre-exists data is very important. So they explore how different pre-training data affect the model reasoning for math. And it's true, pre-training data is important and it's improved the performance. So they have a case study. Case study. Come on. Yeah, let's see. Before case study, let's see this figure. Impact of pre-training model choice on mathematical reasoning performance, right? So they say that, okay, there are different models which is trained on more mathematical reasoning and less mathematical reasoning. So this blue one is where we train for math 500 is more mathematical reasoning, and here it's not. So here you can see is the base is the worst. So generally like this, instructors train on more mathematical problems. This 32 billion chat is not. So pre-training knowledge not here more bad performance. Pre-training knowledge here more good performance. Simple. But I think this case study is more important and more knowledge rich. So let's see. They compared LIMO trained AI with other large language models, DeepSeek R1 and Quen 2.5B, etc., etc. So LIMO demonstrates stronger step-by-step reasoning. LIMO checks its own work and correct mistakes during problem solving. Let me zoom in. So, There's this problem, right? Every morning, Aya goes for a 9 kilometer long walk, stops at coffee shop, etc., etc. This is a math problem, right? And it asks, okay, Quen 2.5, 32 billion instruct, solve this problem. DeepSeek R1 solve this problem, and LIMO train Quen model, please solve this problem. What happens is that LIMO checks its own work and corrects mistakes during problem solving. It allocates more explanation to complex steps, make reasoning more explicit. It uses self-reflection technique like, wait, let me verify this step. And after that, what? Going 2.5, 32 billion instruct fails to correct wrong calculations, making logical jumps instead of breaking down problems, which is bad. DeepSeek R1 shows some reasoning availability, but lacks explicit verification steps. I don't know if you guys can see it, but see, unable to correct the false statement above, did not verify the cross-verify equation 2. But here, both have the self-reflection, detailed steps calculation, think of anthropic tone, etc. Like, okay, wait, 24 minutes hour, no, 60 minutes an hour, something like that. DeepSeek R1 does this very easy in chat. If you try to see the DeepSeek chat when you conversate with him, it has this, okay, wait, no, I believe the thing, etc., which is very good with DeepSeek, I believe. But it would be very interesting to test it with this O3 Mini, etc. But yeah, I think that's it. And evolution of the mathematical reasoning LLM, they say that, okay, how evolution of the mathematical reasoning increase. Now we are on the different scenario where we have LIMO with self-training capacity, etc. Then we have this test time scaling and long change reasoning, which generally specify, okay, now we have the capability to run it on the inference time. We can have a long chain reasoning, LLMs can understand, etc. So generally they say that. And also that they say that data quality level 5, this is how much average token per response it take, top frequent occurring keywords. Wait, you can see as soon as the average token response goes, etc. It goes, okay, wait, therefore, which number sense. But yeah, it's like this. And they also say that this is very interesting, right? Instead of focusing on scaling model parameters and training data, recent work has shifted to exploring test time scaling. And how you can do it, it's like parallel sampling and symbolic tree search to enhance the reasoning availability. Then he says that how O1 is trained, like long chain of reasoning thought, self-reflection, verification, backtracking, process commonly employed by humans when solving complex problems. It says that, okay, this cognitive thinking, the process can increase the model performance, and O1 is also using. And this data efficiency. Like, however, whether this lesson can be applied to reasoning tasks remain uncertain, like giving potential high computational complexity of such tasks. Says that, okay, can we employ it in another domain, etc.? Does it will make sense using this? But yeah, it's like this only. I think in the code they explain it in more detail, how they train it, etc., etc. But in the paper, it's like this. Then future works are very interesting in this, as much as I'm seeing here. So future works goes like this: domain generalization, theoretical foundation, automated assessment, multimodal integration, real-world impact, and cognitive science bridge. So let's see what it is. So domain generalization, right? LIMO hypothesis is the broader reasoning domain representation network. So high quality reasoning chains could potentially generate scientific reasoning, logical detection, and causal interference. So we should have a domain generalization for this. So next part is theoretical foundation. So formalizing the relationship between pre-training knowledge, inference time, and computational and reasoning capabilities, right? And investigating the minimum threshold for pre-trained knowledge. So what could be the minimum threshold of pre-trained knowledge that could be there so that this reasoning skills could work? That is the theoretical foundation they agree on. And automated assessment, right? Created automated system that can evaluate and improve the reasoning chain quality based on a proposed matrix. I think could be solved in upcoming 1 or 2 years, I believe. And multimodal integration, which I think is very important. Cross-model reasoning. Develop quality matrix for this cross-model reasoning chains. But this cross-model reasoning is very interesting. So we can run OpenAI O3 Mini, I believe, and with this Quen instruct with LIMO and see if they can fight and improve its solution or something like that. And then real-world impact, adapt to real-world practical performance, real-world problems, solving other things, and then cognitive science bridge. This is the best part. Understanding the parallels between LIMO reasoning patterns and human cognitive process, and could inform the development in more effective reasoning strategies. and incorporating cognitive science principle into design of reasoning chains. Maybe some psychological theories of papers on how humans think of the problem, etc., could improve its thought thinking process. Or we can say, okay, this guy thinks like that, he's in this field. Maybe doctor thinks like that, their cognitive skills is Z, X, Y instead of X, Y, Z. So something like that. So ZXY thinking should be done in the medical professional engineering principle. It should be think like that. This is how the cognitive skills work. But I think that's it. Like they acknowledge the people. This is the reference, which I think it's the gold mine. If you want to know about more paper, etc., it says very good paper, etc. But this is LIMO. Less is more for reasoning. And yeah, thanks. Any questions, please? Let's discuss reasoning. Let's just go on.
Yeah, wow, very good choice of paper. Very timely. We have to deal with a bunch of stuff like this right now. I maybe I can make a comment on how it aligns very well this what you showed here with what we've been finding, trying to do reinforcement learning with these models, and is that these small. I mean, during the reinforcement learning stage, I have this mental model that it's doing two things. One thing is trying to discover new ways of thinking, good ways of thinking. And another thing is trying to learn how to use these ways of things that you learn, right? And it appears that these small models like 7 billion parameters, stuff like that, they're actually terrible at finding new forms of thinking. Like it takes so long. It's too much RL time of training and a lot of money. Uh, but they're actually quite good at copying the behavior if you give it, right? Which is what's been shown here. And it really opens like a new way of thinking about it, right? Maybe I don't know, maybe we can even think about really searching like through the space of possible reasonings for a given problem, right? This curatorship that you did, that the paper says it did, right? This 800 training examples. Like search a bunch of reasoning patterns to try to solve a problem, maybe find some ways of reasoning that are very good, and then you give it to the smaller models, right?
So right now you're saying instead of this, these it said like 817 curated samples of math problems. So 800 curated samples of reasoning.
No, what you did, they're already doing it, right? These 800 samples, they
Mhm.
capture reasoning patterns. They're
Yeah,
very,
reasoning
very good.
patterns for
Yeah,
samples.
yeah.
You're saying for our problem we could have a reasoning, right? What proper reasoning would could be. So out of 800, let's see, 17th is we have a reasoning for it. So you're saying how we can do the reasoning there, right?
Yeah, yeah. For arbitrary tasks, right? For
Yes.
landing or whatever, we can
Mhm.
like search the space of possible reasonings and find like very good examples of reasoning in that domain. That'll be
Mhm.
very, very interesting. And yeah, because again, because these small models, they're not very good at creating their own highly curated examples, right? They're not very good at just finding it out. Yeah.
Yeah. No. What else? What else, people?
I have to say that's really impressive how like less is more, right? The difference in results, right? It's I think like people are like, oh, if you put too much data, maybe it's not a good like, especially if it's like AI generated. I think I heard like some concerns about that, but I don't remember like actually focusing on quality, right, rather than quantity. At least for LLMs, text models, right? Impressive.
Yeah, it's like we are going back to data centric AI, right? Which was very hyped
Yes,
for LLM, right? Coming back to
yes.
that thing.
Yeah, because like before we have like the proto LLMs BERT and the others was like, yeah, but the data will complete the the gaps that you have on like man-made data sets, right? So it's like you get like things, and I think this is like the other way around.
Yeah.
Very interesting. Yeah. Henrique?
Yeah, I was actually talking to Aaryan right before we started, and I agree. And I actually, after seeing the presentation, I think that is even stronger. This, the conclusions here of this paper, I think they can be generalized not only for LLMs and AI in general, but for us as well. I would argue that the idea that we sometimes overthink and over engineer solutions, and actually less is more in reasoning for us as well. I'm actually convinced of that. Very cool paper, very provocative.
Nice. Yeah. Using it in real life. Yeah. Yeah, I really like this. I don't know where we'll go with this because it's a very recent paper, 5 February. And I think Lucas sent some one link in having phase. They are discussing this. I think someone is retraining the models with this. But yeah, it would be very interesting to see where this will go and what comes out of this on top of this paper, how they are going to reflect. So this will be like reinforcement learning, and maybe another DeepSeek paper would come. Less is more for reasoning trained with LIMO or something like that. But yeah, who knows?